In this lesson, we're going to take a look at nuclear reactions. Now, we've talked about radioactive decay and how unstable nuclei will decay into more stable nuclei. But now we're going to talk about why that's occurring. Remember, just like everything, chemical reactions occur because atoms are making new bonds, and they make new bonds to become more stable. Well, nuclear reactions, nuclear decay, these occur because, again, we're trying to make things more stable. More stable means getting rid of excess energy. So, in nuclear reactions, we have two forces that are really fighting with each other on what's going on, what's causing all this energy. And you can think of forces as pushes or pulls. And there's two forces in the nucleus. Protons have a positive charge, which means there's an electric force there, and electric forces are going to repel because like charges repel. So protons have this force acting on them that's trying to push them apart, and this gives them some potential energy. It's like compressing a spring that wants to spring apart. But there's also the strong nuclear force, which is an attractive force between protons. So it's like a spring that when you stretch it wants to snap back together. So these two forces are both acting on protons, but they affect them differently. The strong nuclear force can only act over very short distances, only over about one proton. The electric force can act over a larger distance than that. So if the two protons are too far apart, so here's a proton and here's a proton, this distance between them is so great that it's the electric force that's going to have the bigger effect, and so these protons are going to be repelled. But if you had two protons this close together, there's still that small repulsion force from the electric charge, but there's a very, very strong nuclear force trying to pull those two things together. And since the strong nuclear force has a greater effect in that case, more stable would put it closer together. In this case, where you had two protons farther apart, more stable means getting those things further apart. So, if two protons are sufficiently close, the strong nuclear force binds them together. Otherwise, the electric force is going to repel them. So these two forces, they're in a constant fight trying to decide which one's going to win. And since it's the distance between the protons that has the biggest effect, it's actually the size of the nucleus that's going to determine who wins this fight. So, for the large nuclei, we have this thing called nuclear fission. In a large nucleus, which is more than 26 protons, and most things that undergo nuclear fission spontaneously have much more than 26 protons, the distance between adjacent protons is large enough that the electronic force of repulsion has a greater effect. So remember, in the nucleus, there's protons and neutrons, and the neutrons help to stabilize it if there's the right amount. And so you have protons that are going to be pretty close to each other, and the strong nuclear force holds these ones together, and these ones together, and these ones together, and these ones together, and you got these ones and these ones and these ones. But this proton and this proton, they're more than two protons apart. There is the electric force of repulsion trying to push those apart, and it has a greater effect than the strong nuclear force between these two things. So when you have lots of protons in the nucleus, the electric force of repulsion has a pretty big effect, and that actually causes the nucleus to break down. And if that happens, then we end up with two or more smaller nuclei, and that's called nuclear fission. A fissure is a crack. It happens when things break apart. So nuclear fission occurs when two or more, or when one nucleus breaks apart into two or more smaller nuclei. The overall mass number before and after the reaction is going to remain the same. So if you had like uranium-235, that 235 is the mass number. When it breaks apart, it goes, I think it goes to thorium-231, and then you also get helium-4. Okay, that adds back up to 235 total nucleons, but the actual mass goes down. So one atom of uranium-235 is going to actually have more mass. It's going to weigh more than these two things together. That means that nuclear reactions don't follow the rules of chemical reactions. In chemical reactions, you can't create or destroy matter. In chemical reactions, you can't create or destroy energy. Well, in nuclear reactions, it turns out matter and energy together are conserved. So while you can't create or destroy energy or matter, you can actually convert energy into matter and matter into energy. That's Einstein's equation, E equals mc squared. So the mass that we lost is not actually gone, it's just in a different form. It's now in the form of energy. So nuclear fission actually allows us to convert mass into energy. That's Einstein's famous equation, E equals mc squared, where E is energy, m is mass, and c is the speed of light squared. Now, that means very, very little mass can produce lots and lots of energy, because remember, c is the speed of light, which is 300 million meters per second. And if you square that, you're up to 9 with like 18 zeros after it. Okay, so that's a big number. So very, very small amount of mass, when it's converted into energy, gets you a large amount of energy. And that's the principle that nuclear reactions rely on. So because there's so much energy and a little bit of mass, we can get out a lot of energy from a little bit of mass. Nuclear power plants, nuclear reactors, they use that to use a very little bit of radioactive material to get out huge amounts of energy. And in fact, the first nuclear bombs that were developed were fission bombs. And I think the first one had like 5 kilograms of polonium in it and produced the same amount of energy as 18 or 19,000 tons of TNT. So about 11 pounds of radioactive material contains the same amount of energy as 19,000 tons of dynamite. Nuclear energy is much, 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 much more higher quantities than chemical energy. So nuclear fission powers nuclear power plants. We use that energy to heat water, and that makes it steam, and then the steam drives turbines, and that creates electricity for us. Nuclear fission in the Earth's core keeps it hot, and of course that drives convection currents in the mantle, which drives plate tectonics and keeps the continents drifting, volcanoes and earthquakes and things like that. Now, the opposite can happen if we have smaller nuclei. So in nuclear fusion, we have small nuclei. And that means the strong nuclear force is able to pull protons together. So that means we have protons floating around, and if they can overcome that barrier between them, that barrier due to the electric force of repulsion, then the stronger force is the strong nuclear force, and it's more stable for them to be together. So the protons have to have enough energy to initially overcome that repulsion force. And that means they have to be hot. They have to be moving really, 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 really fast. They have to have lots of energy so that they can actually smash together. But once they smash together, they'll stick together. And this actually goes on in stars. So very high temperatures, remember, that's going to make the particles move faster. It also has the added effect of making it a plasma. So normally a nucleus has its electrons around it, and those electrons are going to repel each other, and you have this cloud of particles in between that's going to prevent stuff from happening. But if you get them hot enough, the electrons gain enough energy to float away, so now you just have the positive nuclei left. And then these are moving fast enough that they actually can smash and collide with each other, and then the strong nuclear force holds them together. That's called nuclear fusion. Thermonuclear devices. The thermo because we got to have the energy to get these things together. The nuclear because once it is, then it's fusion. And this makes heavier elements. So we take 2 or more smaller protons, smash them together, or smaller nuclei, and smash them together to make a bigger nuclei. And just like fission can convert mass into energy, fusion also converts some mass into energy. So again, if hydrogen were to fuse, so hydrogen 2 were to fuse with hydrogen 2, we'd get out helium 4, 2 protons, 2 neutrons. The total mass number before and after is still the same. 2 plus 2 is 4, but we're actually going to have helium 4 going to have a little bit less mass than these two things individually. Okay, so again, it follows the same rules, E equals mc squared. Now there are no nuclear fusion power plants, which is sad, because when you have nuclear fission, the result is usually another radioactive material that you have to deal with. When you have nuclear fusion, the result is helium. It's not radioactive. There's very much less radioactive waste, and there's an abundance of hydrogen. We can do this with lots of things if we can figure out how to get nuclear fusion to work. But since it requires very, very high temperatures, we have to put in a lot of energy in order to make nuclear fusion occur. But it does occur naturally in some places. Stars carry out nuclear fusion. So when you look up in the sky at night, or you see the sun in the daytime, that's not actually on fire. That's nuclear fusion occurring. Most stars are fusing hydrogen into helium, and then some helium into some heavier elements. They can fuse everything up to iron, but they can't go bigger than that, because remember, to get things that are bigger than iron, well, that's when fission occurs. So how do we get elements that are heavier than iron if we if stars can't do it? Well, it turns out stars can actually produce elements heavier than iron, but not in their normal life. Okay, it happens when stars die. If a big enough star explodes, we get what's called a supernova, and that produces enough energy that it can actually force the smaller nuclei together into bigger, heavier nuclei. It requires the addition of energy. So the energy released smashes these nuclei together, and we get all the elements from iron to whatever we get. And then that energy that's stored in those large nuclei is released through the fission process. So fusion and fission are opposite processes. Fusion is trying to build up smaller nuclei into larger nuclei, and fission is trying to take large nuclei and tear it down into smaller nuclei. And it's due to these forces, the strong nuclear force trying to hold things together, and the electric force of repulsion between protons trying to push them apart.